Hello, hello, hello! We're going to do a little de Broglie here. Now, de Broglie took Einstein's theory and turned it on its head. Einstein said that light was a wave and a particle. De Broglie said, well, if waves can be particles, can particles be waves? He started out with electrons, but we've gone further and further and further, and pretty much we find that any particle can be a wave. So, I'm a particular person. Can I be a wave? What would be the wavelength of me if I am a particle? So, anyway, let us get started. So, here's de Broglie's theory. De Broglie's theory says that lambda, the wavelength, is equal to Planck's constant over the momentum. Now, you'll remember that momentum is, in fact, capped marker. Momentum is, in fact, mass over mass times volume, or mass times velocity. So, what is my mass? Well, let's just start filling in here. Lambda is equal, now, we're going to use the Planck's constant, that is in joules to second, so that is 6.63 times 10 to the negative 34? Negative 34, that's a good number. Over my mass, 108.9, I'm probably heavier now, times my fastest speed, which was 5.6 meters per second. So, we are going to figure out what would be my wavelength. Now, just kind of going through here, let's leave Planck's constant alone for now, times 10 to the negative 34, but let's get our momentum, 108.9 kilograms times this, and I think I got 609.84. Not that that matters that much. It's going to be kilograms meters per second squared. I'm leaving the units out because, quite frankly, we'll go crazy. So I'm going to leave the units out. Divide them, and I get lambda is equal to 0.0109 times 10 to the negative 34. So I just divided 6.63 by 600. I got about 1/100th. And you just bring this down. Now, in scientific notation, you always want to make sure that your decimal point is right after the first digit. So 1.09. Now, I made this 2 orders of magnitude larger, which means that I need to make this 2 orders of magnitude smaller. If this gets 100 times bigger, this has to get 100 times smaller for it to be the same number. And there we go. And by the way, our units here are meters. Now, how small is this? I can't even begin to express. I cannot show you how small this is. Not just because it's microscopic, but because it's actually impossible. Just like there's quantums of energy, quantums of mass, quantums of light, there is quantums of length. There's length where you cannot get smaller. A Planck length is as small as you can get. You can't have half a Planck length. Just like you can't have half an electron, you can't have half a photon, you can't have half of a quantum. But here's the thing. A quantum is about 1 times 10 to the minus 35. So my wavelength is 1/10 of a quantum, but you can't have anything smaller than a quantum. So can I ever show you this? No. Can we ever measure this? No. In fact, is it even possible for something to be that small? No. If you're not 1 Planck length in length, you are nothing at all. There is no length smaller. So yeah, we're never going to prove this. But anyway, we did it. Have a nice day. Bye-bye. Yeah, long story short, the larger you are, the faster you are, the smaller your wavelength, and I'm just too large and too fast.